So I've got a little slide here with 4 pairs of slits in it. I'm going to put this up on the overhead to get a larger view of it so we can see what it looks like. So here we go. We can see we've got 4 pairs of slits. They are very, very narrow openings, less than 1 millimeter across, and they are very close together. This is a greatly enlarged view. Now what I'm going to do is I'm going to take a single laser and pass it through one of these pairs of slits and project it up onto the screen, and let's see what we get. Okay, so first here's the laser without going through the slits, just the laser unaffected. Now I'll put the slits in front of it. There we go. All I've done is put the slits in front of the laser, and now we have this pattern that's spread out along a horizontal line where, notice, we've got these series of bright dots with dark spaces in between. Now, the bright dots, what are those? That must be where we have light combining with light to give us lots of light. In other words, constructive interference. But these dark spaces, where are those coming from? Those must be formed where we have light from one slit plus light from the other slit that are actually canceling each other out and giving us no light. In other words, destructive interference. And notice, what do we have? We have constructive, destructive, constructive, destructive, constructive, destructive. In other words, in the very center where the central axis is, that's where the 2 rays would come together with no path difference. In other words, d sine theta equals 0. So right in the center, d sine theta equals 0. Then the first dark area. Now, the term that's used are called fringes. The bright spots are called bright fringes. The dark areas are called dark fringes. So the very central bright fringe, that's where we have 0 path difference. That first dark fringe, that's where the path difference is 1/2 lambda. The next bright fringe, path difference is lambda. Dark fringe, 1.5 lambda. Next bright fringe, 2 lambda. Next dark fringe, 2.5 lambda. Very, very good. Excellent. Now, let's go back to the drawing, but one thing I want you to notice is we've got this bright fringe, dark fringe, bright fringe, dark fringe structure here, but also we've got this central area that seems to be brighter, and then it gets darker over here, and then brighter over here, then darker, and then brighter and darker. And the same thing on the other side. Darker, brighter, darker, brighter. We'll take a look at that next time. Right now, the double slit interference pattern is what's causing the bright fringe, dark, bright, dark, the very small pattern that we see there. Okay, let's go back to the picture, to the drawing. To give you a very simple idea of what's going on with this double slit interference pattern, let's imagine you have a source of rays. Let's just imagine this is like the source right here, and it's sending out waves in all directions. This would be very much like dropping a pebble into a body of water, and you get the ripples extending out in all directions. Now, in our situation, you can think of this as basically cutting off part of, or 1/2, where this little opening right here, that's where the slit is. So the light is coming from the laser over here, hitting the screen, hitting a slit, and then going off in all directions like that. But I'll just take that off so we can look at the whole thing. Now, this is a 2-slit interference pattern, so I'm just going to add another one of these on top of it. There we go. And what do we get? Well, we get basically the double slit interference pattern. Notice, here are the 2 slits, and imagine the light is coming this way. Well, what do we have along this line right here? We've got dark lines on top of dark lines, light lines on top of light lines. We have constructive interference. If we had a screen over here and the light was shining this way, we'd get a nice bright spot right here, constructive interference. But what about this line right here? We've got light lines on top of dark lines on top of light lines. What's going on along here? We're having destructive interference. So on the screen, along this line, what would we find? We find a dark area, a dark fringe. Bright fringe, dark fringe. And then again, along this line, a bright fringe. Along this line, on the screen, dark fringe. Bright fringe, dark fringe. Bright fringe, dark fringe. Likewise, dark fringe, bright fringe. Dark fringe, bright fringe. And we can change that pattern by changing D. In other words, by changing the distance between the slits. So as we change the distance, we change the pattern. And as we increase D, we get more and more of those slits, a smaller and smaller pattern over here. Bright, dark, those fringes get closer and closer together. Great, let's go back to the mathematics. So what we saw on the screen then is at the very center, we end up with this bright spot, that central bright fringe. Then there's a dark region, and then another bright spot next to it. Then a dark region, another bright spot. And the dark region, in other words, dark fringe, bright fringe, dark fringe, bright fringe, dark fringe, bright fringe, etc., etc. Now, we also saw all of this on the other side of the central axis. So we also have these bright fringes down here. Now, in our equation, we might think of that as negative theta, theta below the central axis. That's just where the top ray, in this case, would be longer than the bottom ray. So that would be theta, where theta is negative, or where m is -1, -2, -3. Likewise, down here, -1, -2, -3. Okay? So, here, let's think about what values of m give us these particular fringes. Well, for the bright fringes, the central bright fringe, that corresponds to m equals 0 in our bright fringe equation. The next one is m equals 1. The next one, m equals 2, m equals 3, etc., etc. If we wanted to look at the fringes below the central axis, this would be m equals -1, m equals -2, m equals -3. Okay? Now, what about the dark fringes? The first dark fringe, that's where the path difference is 1/2 lambda. That's actually where m equals 0 for the dark fringes. So this would be the m equals 0 dark fringe. First dark fringe. The first dark fringe is m equals 0 from our equation. The next dark fringe corresponds to m equals 1. The next one, m equals 2. On the other side, the first dark fringe on the other side of the central axis would be m equals -1. So it's not exactly symmetric. The reason is because we actually used a form of m plus 1/2 lambda. So the first dark fringe corresponds to a path difference of 1/2 lambda, and that's actually where m equals 0. We could have said m equals, this equals m minus 1/2, in which case the first dark fringe would be m equals 1, because 1 minus 1/2 is positive 1/2. But by convention, we'll just write it as m plus 1/2, so that the first dark fringe above the axis actually corresponds to m equals 0. Okay, very, very good. Let's stick some numbers in here. Okay, now let's keep in mind that for the double slit experiment, we have two different equations. One equation that tells us where the bright fringes are, one equation that tells us where the dark fringes are. The bright fringe equation is d sine theta equals m lambda. The dark fringe equation is d sine theta equals m plus 1/2 lambda. And remember, m could equal 0, plus or minus 1, plus or minus 2, etc., etc., any integer. Now, let's imagine we do an experiment and we get some measurements and we want to do a calculation. So let's try that. So let's imagine we have the following setup. We have a pair of slits. We have a light, a laser, coming through the two slits that is forming an interference pattern on a screen, and the screen is, let's say, 4.50 meters from the slits. Now, the distance between the m equals 0 and m equals 1 bright fringe, in other words, the distance between the central axis, that's where the m equals 0 bright fringe is, and the m equals 1 bright fringe is, let's say, 3.70 centimeters. Now let's say the laser we're using is a 490 nanometer laser. But we don't know what the slit separation is. We don't know what D is. Let's see if we can actually calculate what that is. Well, we know that the distance from the central axis to the m equals 1 bright fringe, in other words, the position of the m equals 1 bright fringe is 3.7 centimeters from the central axis. So, the angular position theta of that bright fringe would be, well, we can use tan theta in this case. Tan theta is equal to, opposite, putting both of these in meters, 0.0370 meters over 4.5 meters. Dividing that out, we get 0.00822. Taking the inverse tan, we find that theta is equal to 0.471 degrees. So that's the angular position of our m equals 1 bright fringe, measured from the principal axis, the central axis. So we know that for bright fringes, d sine theta equals m lambda. In other words, d must equal m lambda over sine theta. So we can put in our numbers. For that fringe, m equals 1. Lambda is 490 nanometers. 490, remember a nanometer is 10 to the minus 9 meters. Divided by sine theta, and theta we calculated to be 0.471 degrees. Multiply that out, and we find that d is equal to 5.96 times 10 to the minus 5. In other words, around 60 microns. Okay, very, very good. Excellent. Now, is there any other way that we might be able to get two sources of light to be able to come together and give us either constructive or destructive interference? Is there another way that we can form two coherent sources? Well, there actually is. There is another very, very simple way, and that uses reflection.